Let's have a look at partial elasticity in this question. So we're given a function and we want to find out the partial elasticity. Now first, what is partial elasticity? What is this going to show us? This is going to show us the percentage change in the result when the input increases by 1%. So in our case, the input of the function is x, and when this increases by 1%, how does f of x change also in percent? So let's do it. What is the partial elasticity with respect to x? Well, that's going to be equal to x divided by the original function times the derivative of the function. We know x, we know the function, we must find out the derivative, and this is going to be the hardest thing. So let's do it. F derivative with respect to x is x to the power of 3 times 2x to the power of ln of x, all of this thing derivative with respect to x. Now we have a product, which means that we will apply the product rule. So we have the derivative of the first term, x cubed derivative with respect to x, times 2x to the power of ln of x plus x cubed times the derivative of the second term with respect to x. So 2x to the power ln x derivative with respect to x. Okay, let's see what else we can solve here. Let's make some space. X cubed derivative with respect to x, that's just gonna be 3x squared. So power rule, 3x squared times, from here we just write 2x to the power of ln x plus x to the power of 3 times this derivative, which we still do not know. And this is a bit of a tricky derivative because we raise it to the power of our variable of interest. We raise it to the power of ln x. And whenever we have questions with logarithms, it's always useful to solve them separately by making it into a function. So this is going to be just a new function, because if we give different values of x, we get different results. So it's literally a function of x. And let's call that function y. Y equals to 2x to the power of ln of x. Now we notice here that we have the logarithm and we have the y. So whenever we have this relationship, it's useful to work with logarithms. We can take the natural logarithms of both sides and we will see that we can apply the properties of natural logarithms. That's why we do it. So let's write ln and ln of this side, and let's just keep other color for the rest. Ln of y is going to be ln of this thing, 2x to the power ln x. Now recall the property of logarithms that we can take the power down. That's why we do it. So let's keep going. We would have the logarithm of y. And by the way, let me just write the general formula in case you forgot. That's ln of a to the power of x. So whenever we have an expression to a power and we take the natural logarithm, we can take the power down. So x times ln of a. Okay, let's keep going here. Ln of y is equal to, take the power down, that's ln of x times ln of 2x. These are the inputs of the logarithm. Okay, now remember that what we actually want is to take the derivative of 2x to the power ln x. So if we take the derivative of 2x to the power ln x, it means we take the derivative of this side and the derivative of this side. So if we start differentiating, this and this is the same as differentiating this and this, because it's an equation. So what we do on one side, we do on the other side as well, meaning that we're taking the derivative of the left side equation, meaning we're differentiating the right side as well. So let's keep going. What is the logarithm of y derivative? Remember that y is a function of x, so we have a chain rule over here. We will differentiate y, which gives us 1 over y. So we have 1 over y, but then y is a function of x, so we have to take the derivative of y with respect to x as well. And now here we have a product again, so we're going to apply the product rule one more time. Ln of x derivative times the ln of 2x plus ln of x times the ln of 2x derivative with respect to x. Let me write with respect to x so we keep track of what we're differentiating. Let's keep going. So we have y derivative with respect to x divided by y is equal to, what is ln x derivative? It's just 1 over x times ln of 2x plus, here we have ln of x times, what is ln of 2x derivative? That's 1 divided by 2x times 2x derivative, because of the chain rule, it's an expression of x, and 2x derivative is going to be just 2. Okay, let's see how we continue here. Make some space. We have still y derivative with respect to x divided by y is equal to, now 2 and 2 cancel out, and we would have ln of 2x divided by x plus ln of x times 1, so it's just plus ln of x. Now we need just the derivative of y with respect to x, because once again, let's not forget that derivative of y with respect to x is the same as the derivative of 2x to the power ln x. That's what we're looking for. So let's keep y derivative on one side only, y derivative with respect to x, and if we keep this on this side, by using the product, cross multiplication, we just multiply y with this entire expression. So we will have y times ln of 2x divided by x plus ln of x. Now what was y? Once again, going back, y was 2x to the power ln x. So let's substitute it. Let's substitute it. So we have y derivative with respect to x is equal to 2x to the power ln x times this fraction, ln of 2x divided by x plus ln of x. Okay, what still we can do here? We can use it, we can use this derivative to substitute into our derivative of the function. Let me zoom out so we can actually remember what we're doing, because I admit this is a pretty lengthy question, so it's not easy to keep track, but it's the way it is, so gotta do it. Now this is y derivative with respect to x, but remember that y derivative with respect to x was the same as the derivative of 2x to the power ln x with respect to x. And now we want to take this thing. Let me see if I zoom out once again and substitute it so it's clearly visible. We take this thing, zoom out, and we're substituting into the, over here, this was what we were looking for, ln of 2x. So this was the derivative that we were looking for. Let me just see, wait, it's over there. I don't know if it's visible or not, but I'm gonna zoom in a second so you'll see what's going on. We are substituting this into the derivative of the function, which goes over here, yes, which goes over there. And now I'm gonna zoom in and you will see what's happening. So zoom in, this is where it's going, hope it's visible. So the derivative of the function f prime x, we're here, f prime x equals to this whole thing. We did the product rule, and we are at this point where we're substituting 2x to the power of ln x derivative. So let's keep solving over here. We'll need some space, so I'm gonna go a bit to the right. But first let's just write that we are solving for the derivative of the function, which is 3x squared times 2x to the power of ln of x plus x to the power of 3 times, and is the result of what we just did, and that result is equal to 2x to the power ln x, 2x to the power ln x times, and in brackets we're left with ln of 2x divided by x plus ln of x over x, ln of x over x. In just a second, let me quickly go back to the question just to see if it's indeed right. Yeah, this was a small mistake. Let's correct it real quick. here when we cancel the 2 and the 2, we're left with 1 over x, but I only left 1, so it's ln of x divided by x over here. So it's divided by x, my bad, I'm sorry, divided by x. Okay, so here we have it, divided by x. Now what do we notice? Both fractions are divided by x, meaning we can take the division, which is the same as multiplying with 1 over x, as a common factor. So we will take 1 over x as a common factor over there, so we can cancel some stuff out. We will have 3x squared times 2x to the power of ln x plus x to the power of 3 times 2x to the power of ln x times, and let's take now 1 over x as a common factor, and in the brackets we're left with ln of 2x plus ln of x. Make some space, go to the right, yes, hop, hop. So change colors. Now what do we have? X to the power 3 and x, they cancel out. 1x from here, 1x from there. Let's see what we're left with. F derivative with respect to x is equal to 3x squared times 2x to the power of ln x plus, here we're left with x to the power of 2 because we cancelled 1x out, times 2x to the power ln x times ln of 2x plus ln of x. Okay, let's see how we can keep going over here. This is the derivative of the function, and remember that this is still just part of the question because we have to substitute this into the elasticity. We are still solving for the partial elasticity, and this was just the derivative of the function. So if we substitute this into the partial elasticity with x, we said that's going to be x divided by the original function, and the original function was x to the power of 3 times 2x to the power ln x, and now we can use the derivative that we just found, and that's 3x squared times 2x to the power ln x plus x to the power of 2 times 2x to the power ln x times, and here we have ln of 2x plus ln of x. Yes, that seems to be right. Take it in brackets, and let's see what we can do right now. What we can do right now is to open the brackets and multiply x with every term. So we can multiply x with the first, we can multiply x with the second, meaning that the partial derivative is going, the partial elasticity is going to be equal to x times 3x squared, that's 3x cubed multiplied with 2x to the power of ln x, plus x times x to the power of 2 is x cubed multiplied with 2x to the power of ln x, multiplied with ln of 2x plus ln of x, keep this in brackets, divided by x to the power of 3 times 2x to the power of ln x. Now what we can still do, we can write this fraction as two fractions. We can write it as a sum of two fractions with the same denominator, and we do so because we'll cancel something out. So let's write the first term, that's 3x cubed times 2x to the power ln x divided by our denominator, which is x cubed times 2x to the power ln x, plus from here, plus the second term, which is x cubed times 2x to the power ln x times this multiplication, which is ln of 2x plus ln of x, divided by the same denominator, which is x cubed times 2x to the power ln x. Let's change colors and show what we cancel out. I think you can see it. X cubed and x cubed cancels out. 2x to the power ln x cancel out on both sides. Check over here, x cubed, 2x to the power ln x, 2x to the power ln x. What are we left with? We're left with the partial elasticity with respect to x equals 2. 3 plus ln of 2x plus ln of x, ln of x. And let's see, can we do something else? What we can do, still something, just to make it even more nice, 2 times x under the logarithm, we could apply a logarithmic property, which is ln of a times b is equal to ln of a plus ln of b. So we could write ln of 2 times x as ln of 2 plus ln of x. So the partial elasticity is equal to 3 plus ln of 2 plus ln of x, and this is this term over there, plus ln of x. And we did so because now we can group the ln of x together. I think that's just gonna look better. Partial elasticity with respect to x is equal to 3 plus ln of 2 plus 2 times ln of x. And that's it. That's as much as we can do. We are done. I know it's been really long, but it's good training for this partial elasticity. At the end of the day, it's nothing complicated. It's just a matter of, you know, mechanics. Basically, we do the first derivative of the function, we keep track of everything, and then we just substitute it into the partial derivative with respect to x. Make sure that you keep track of everything right, because usually things have to cancel out. So if you have some, you know, weird numbers, hold on for a second, look at it again, and try to have, you know, neat fractions, try to take out common terms, and things get smoother and smoother. Hope this helps. We are done.